Hello all. In the previous video, we learned two ways of determining a plane. In type 1, we were given with 3 points and we determined the plane. And in the type 2, we were given with the perpendicular distance from the origin and the normal vector. Now in type 3, we can determine the equation of plane where the perpendicular vector is given, that is a normal vector to the plane is given, and a point through which the plane is passing. So with these 2 points given, we can actually determine the plane. So here I have defined a plane, that is 2x plus 3y minus 4z minus 6 is equal to 0. So this is not passing through the origin. So the first condition is we are given with a perpendicular vector, that is a normal vector to the plane, right? So we have a normal vector here which is perpendicular to this plane. So, but the point is this condition alone will not be enough for us. The reason is in space we can actually see we can actually have many planes which are perpendicular to a particular normal vector. So for us to uniquely determine this particular plane what we want, we need a point, at least one point, which is there lying on this particular plane. So if you see, this is the only point, this point is only lying on this plane. So if we know a vector which is normal to the plane, we get all the planes which is normal to this particular vector. But there is only one plane which passes through this point and normal to this particular vector. Now let's try to derive an equation where we are given with a vector which is normal to the plane which we are considering, and a point is given through which this plane is passing. So our n vector is the normal vector to the plane. And let's call a vector, so this point is origin. So let a vector be the position vector of the line of the point through which the plane is passing. PV of the point through which the plane is passing. Okay, so and let's name this also. Let R vector be the position vector of some arbitrary point in the plane. So this point OP is going to be the position vector of P, that is R vector, where the point P is arbitrary. So R vector is position vector of an arbitrary point lying on the plane. So we will start with the vector addition. We have 3 vectors over here. So we can say that OA vector plus AP vector gives us OP vector, right? And rewriting this, we can have AP vector is equal to OP vector minus OA vector. But we already know OP vector is R vector and OA vector is A vector, right? So we have AP vector is equal to R vector minus A vector, where this AP vector lies on the plane which we are considering, right? Lies on the plane. But what do we know? This n vector is perpendicular to this plane, right? So since n vector is perpendicular plane, it is going to be perpendicular to the vector which is lying on the plane also, right? So we have AP vector is perpendicular to the considered normal vector. So that means this implies their dot product should be equal to 0. So we have AP vector dot n vector is going to be equal to 0. Rewriting the value of AP vector, we have R vector minus A vector dotted with n vector is equal to 0. So this is a vector form of the equation where we are given with a perpendicular vector and a point through which the plane is passing. This is vector form. Now let's try to derive the Cartesian form for the same equation. So here I've just changed the name of the point to M because we will be encountering one more A. So there might be an over usage of the alphabet. That's why I've changed the point to M from A. So let us say the coordinate of M, that is a point through which the plane is passing, is x1, y1 and z1, and some arbitrary point on the plane, let the coordinates of that be x, y and z. Let the direction ratios of the normal vector to the plane be a, b and c. So then we know a vector can be represented as x1i plus y1j plus z1k. Then our R vector will be represented as xi plus yj plus zk, and our normal vector will be represented as ai plus bj plus ck. So substituting the values of r vector, a vector and n vector in the vector form, we get this particular expression, and we know on dotting the products we will be multiplying the components of I, components of j and components of k. Doing so, we will be having a times x minus x1 plus b times y minus y1 plus c times z minus z1, that is equal to 0. So this expression what we have here is the Cartesian form of the equation of the plane, where we are given with the normal vector and a point through which the plane is passing.